Hi, my name is Amaya Moro Martín. I work at the Space Telescope Science Institute in Baltimore, and I'm going to be talking to you about interstellar planetesimals. So I am an astronomer, and we astronomers are very fortunate people because we work in a field where sometimes it's much more interesting to be wrong than to be right. And this is because when you get things right, many times you're just confirming what you already know. But when you get things wrong, then things get interesting. And in that process, in trying to understand what went wrong, you may learn very interesting things, sometimes very surprising. Let me share with you one of my interesting mistakes. In late October 2018, we were enormously surprised of the discovery with the PanSTARRS telescope in Hawaii of the first interstellar object crossing the solar system. It was truly the first visitor from beyond. I apologize that I don't have a pointer. The pointer doesn't work while I'm recording this presentation, so you'll have to try to imagine what I'm referring to by, by listening to the description. So this object was about 100 meters inside. It sneaked into the solar system without being seen, approached it from above the ecliptic plane, sank below the plane, and re-emerged very close to the Earth. When we realized of its presence, it was already on top of us. The reason why we knew that this object was a visitor from outside the solar system was because it was traveling way too fast to be a solar system object. Not even the giant planets could have given a solar system object such a kick. It was also crystal clear that this visitor wasn't going to stay because its orbit was clearly hyperbolic. On October 14th, 2017, the day of my birthday, this object was at its closest approach to Earth, only 60 times the distance to the Moon. It came to wish me happy birthday and to tell me you made a mistake. And indeed, I had made a mistake because 8 years earlier, we did a study where we concluded that the chances of discovering one of these interstellar visitors were very bleak. We thought that to detect one, we would have to wait until after 2022, when the Vera Rubin Observatory will start operating in Chile. This observatory, that you can see here in the large image, will be able to photograph all the sky it can see from its location every few nights. It will be able to see very dim objects, and it will detect everything that moves, including many interstellar objects and a huge number of asteroids, comets, and Kuiper belt objects in our solar system. And we made a mistake because the first interstellar object was detected with a much less powerful telescope. This, I'm referring to PanSTARRS that you can see here to the left, approximately to a scale. In that 2009 study, we thought we had understood why nobody had ever detected an interstellar interloper before. We thought this was the case because the number of these objects in space was too low, so that the chance of running into one was also too low. Other researchers agreed. This is why everybody was very surprised by the discovery of Oumuamua. That is how this first interstellar interloper was named, and that in Hawaiian means something like distant messenger who arrives first. What we didn't know at the time was that this initial surprise will turn into utter bewilderment. Now, let me give you a bit of the context. We think Oumuamua is most likely a planetesimal. Planetesimals are the building blocks of planets. They are objects larger than a pebble, but smaller than a planet embryo. Let me remind you briefly how planetesimals form. When a high-density region of a molecular cloud like this one contracts under the effect of its own gravity, it forms a protostar. Around this protostar, there is an envelope of gas and dust that is rotating, and because of conservation of angular momentum, as the envelope contracts, a disk forms around the protostar. We call this a protoplanetary disk. You can see two of them in silhouette here against the bright background of the Orion Nebula. Some of the gas and the dust in this disk falls into the protostar. Some of it's ejected in the form of jets. Let's see what happens to the gas and dust that remains in the disk. This is the disk seen from above. The disk is very dense and its dust particles collide with each other frequently. In some of these collisions, the dust particles stick to each other and form aggregates that grow larger and larger. And you can see some of those aggregates in the panel at the bottom. The growth is very efficient from an initial size of the order of 0.1 microns to particles of the order of a centimeter. This is because the dust particles are tightly coupled to the gas in the disk and their relative velocities and collisional energies are small. This, combined with the microphysical forces like van der Waals and electromagnetic forces, results in very efficient growth. These particles eventually develop from those centimeter grains into kilometer-sized planetesimals, and the processes by which these kilometer-sized planetesimals can become embryos, about 10 times the mass of the Earth, and then planets through collisions and gravitational interactions, are well known. These larger planets are sufficiently massive that they start attracting the gas that remained in the disk, and this can form the atmosphere of the giant planets like Jupiter and Saturn. However, that intermediate stage in which centimeter-sized particles grow into kilometer-sized planetesimals is not well understood because that process seems to be very inefficient. As the particles grow and become less coupled to the gas, their relative velocities and collisional energies increase, resulting in collisions that lead to inefficient growth or fragmentation. In addition, because they experience gas drag, they lose orbital energy and are expected to spiral into the star before they have the opportunity to grow. This difficulty to form objects of about a meter in size is known as the meter-size barrier, and it is a headache in planetary formation theory. Several mechanisms have been proposed to alleviate this meter-size barrier. One of them is the presence of pressure maxima that can trap dust grains, and it is the one that they adopt in this simulation shown here, where is shown the initial stage where you have the dust particles in the top panel, and then the final step where you actually have kilometer-sized planetesimals that have already formed. Another mechanism that will come up later in this story that I am telling you is the presence of low porosity aggregates that favor sticking over fragmentation. As we have seen, planetesimals play a fundamental role in planet formation because they are the building blocks of planets. Planetesimals also play a fundamental role in the dynamical evolution of the planetary system because the disk of planetesimals interact with the planets, causing them to migrate, and this can trigger episodes of dynamical instability and orbit readjustment. This happened in the solar system when it had about 800 million years of age, an epoch called the heavy bombardment. As it can be seen in this video, the orbits of Jupiter and Saturn, here in red and yellow, migrated due to the interaction with the planetesimal belts, and this led to a rearrangement of the orbits and to the ejection of most of the planetesimals in the disk. We can see that again here. Planetesimals also play a key role in habitability because collisions are a hazard, and because planetesimals located beyond the snow line are a source of water and other volatiles to the planets in the terrestrial planet zone. In the solar system, what we know about planetesimals comes from the observations of the asteroids, comets, and Kuiper belt objects. Outside the solar system, planetesimals cannot be observed. However, the dust they produce when they collide or sublimate can be detected and characterized, and the study of these debris disks can help us learn about the underlying planetesimal population. One of the key aspects that we have found from the study of debris disks that trace planetesimals is that planetesimal formation is a robust process that can take place under a wide range of conditions. We have learned this from extensive debris disk surveys that have been carried out with Spitzer and Herschel. These surveys were done in the infrared at different wavelengths. At 24 microns, the surveys are sensitive to dust at approximately 150 Kelvin. That for a solar type star would be the temperature of dust particles located between 3 and 5 astronomical units, which is a distance similar to that of the asteroid belt, and we refer to this as warm dust. At 70 microns, the surveys are sensitive to dust around 50 Kelvin that corresponds to a distance of 30 astronomical units, similar to the Kuiper belt, and we refer to this as cold dust. These histograms that I'm showing you here show how frequently we find debris disk emission around different types of stars. The different colors in the histogram refer to a different type of stars. The mass and luminosity ranges corresponding to these stellar types are shown in the upper left histogram. It is important to note that these surveys are limited by sensitivity. At 24 microns, we are only able to detect warm dust in systems that contain more than 100 times the amount of warm dust in the solar system, while at 70 and 100 microns, the detection limit is between 10 and 20 times the amount of cold dust in the solar system. This means we are only seeing the tip of the iceberg. We find that planetesimal disks exist around stars with luminosities that differ by several orders of magnitude. And we also find debris disks around stars with a wide range of luminosities, of metallicities. And it is from this that we can infer that planetesimal formation is a robust process that can take place under a wide range of conditions. We also find that the planetesimals that are located closer to the stars disappear quickly. And this is because near the stars, the planetesimals collide more frequently and erode away faster than those far from the star. And you can see here by comparing the top histograms that correspond to young stars with the bottom histograms that correspond to all stars. You see that for the all stars, all that warm material, all that warm emission is gone, because that corresponds to material that is closer to the star. But there is yet another reason why planetesimals disappear from a system. It's not only that they erode because they are colliding with each other. These are numerical simulations we made of a system with 3 giant planets and 2 planetesimal belts, an inner belt and an outer belt. In these simulations, we follow how planetesimals grow and how much dust is being produced. The solid line in the insert to the top right shows the emission of the dust as a function of wavelength. The dashed line is the emission from the star. And there is a red band corresponding to the emission that will emit at 24 microns, and the blue band corresponds to the emission at 70 to 100 microns. And I'm going to start the video. So simulations like this tell us that the episodes of dynamical instability and planetesimal ejection, similar to what happened in the early history of the solar system, are very common under many planetary configurations. You see that the planets are evolving here, and it gets to a moment where the planetesimals, there is a dynamical instability and the planetesimals are ejected. So we have seen that the episodes of planetesimal ejections are very common in the planetary system, in the planetary formation process. Other aspects that we have explored another aspect that we have explored is the possibility of transferring these planetesimals that are ejected between different planetary systems. The transfer probability for the solar system today is extremely low because the sun is moving with respect to the stars in its neighborhood at a velocity that is high enough that any entering planetesimal from a young system would fly through in a hyperbolic orbit like Oumuamua did. However, we found that the transfer probability for stars inside a star cluster is 9 orders of magnitude higher than previously thought when considering chaotic quasi-parabolic orbits instead of hyperbolic orbits. These quasi-parabolic orbits are possible in this case because the stars in the cluster are moving at very small relative velocities with respect to each other. And we are interested in stellar clusters because stars are commonly born in there. This movie that I'm going to show you now shows how this transfer can happen. Planetesimals are ejected from the stars shown in green. The green line represents the star's orbit in the cluster. They move in chaotic orbits until one of them, shown in red, is captured by the stars shown in blue. Inside the cluster, the probability of transferring planetesimals between two solar-type stars is 0.15%. This means that we estimate that of the order of 10 to the 14 to 10 to the 16 objects larger than 10 kilograms could have been transferred between our solar system and one of its neighbors before the cluster dispersed. So we are talking when the solar system was very young and it was still embedded in the cluster. This result can have important implications in the context of lithopanspermia. This is a chronological event chart that shows the timeline of events for the Earth at the bottom, for the solar system in the middle, and for the star cluster at the top. Take a look at the central region highlighted in color. At Earth, there is evidence of liquid water near the surface of Earth fairly early on, when the Earth was about 200 million years old, shown as the blue semi-transparent stripe. At the time, there is evidence of a lot of dynamical activity in the solar system, involving planetesimal clearing and heavy bombardment. It is also possible that at that time, the stellar cluster where the Sun was born was still bound. Its dispersal timescale is uncertain, shown as the yellow semi-transparent stripe. The fact that all those factors could have overlap means that, from the dynamical point of view, a window of opportunity existed for the transfer of material between the solar system and other planetary systems in the cluster, and this is very interesting from the point of view of lithopanspermia, if light had an earlier start in the solar system or in other planetary systems in its neighborhood. We have seen how planet formation begins on an orderly fashion, kind of, but ends in a chaos, and how this can fill the interstellar space with planetesimals that are ejected. Another source of interstellar planetesimals are the exo-or clouds, which are objects that are weakly bound to the star. In the case of the solar system, these objects are between 3,000 astronomical units and 100,000 astronomical units. We know they exist because they are the source of the long-period comets, and based on its flux of 2 to 3 a year, it can be estimated that there are about 10 to the 12 objects larger than 2 kilometers in the solar system's Oort cloud. When a star reaches the end of its lifetime, it loses mass, and as a result, the objects in its Oort cloud that were weakly bound to the star are released into the interstellar medium. They can also be released due to stellar encounters. With all those planetesimals in interstellar space, it was expected that sooner or later, the trajectory of one of them would cross paths with the solar system, becoming an interstellar interloper. And as I mentioned at the beginning of the talk, about a decade ago, we estimated the number of interstellar planetesimals per unit volume using our knowledge of star and planet formation, and we found that this number density would be so low that the detection of one of these interstellar interlopers would require the deep surveys of the Rubin Observatory planned to start in 2022. And other authors confirmed that prediction just a few months before Oumuamua was detected. So let me pause here to emphasize that interstellar interlopers give us an extraordinary opportunity to study planetesimals from other planetary systems. Once ejected into interstellar space, the interstellar planetesimals would drift for millions and millions of years, and in the deep freeze of the interstellar medium, they would remain unaltered, like time capsules from their planetary system's most distant past. Let's talk about the number density of interstellar planetesimals. The number density of interstellar planetesimals is higher than expected by 2 orders of magnitude. I have tackled this problem in different ways using detailed population studies, and I still cannot account for the number of planetesimals that are supposed to be out there. On the one hand, we have the observations, and on the other hand, we have the expectations. Regarding the observations, we know that Oumuamua passed within 0.4 astronomical units of the Earth. We also know that PanSTARRS had only been operating for a few years, and from this we can estimate that there are about 10,000 interstellar objects like Oumuamua within the orbit of Neptune, assuming that objects like Oumuamua are uniformly distributed. Regarding the expectations, we can calculate the number of interstellar planetesimals per unit volume of space based on the observed number of stars per unit volume and making an estimate about how many planetesimals each star can eject. There are many uncertainties in this calculation, but a generous upper limit would imply that within the orbit of Neptune there would be about 100 objects at a given time. This is 2 orders of magnitude smaller than observed. This discrepancy points out that we still have a lot to learn about the population of interstellar planetesimals and their origin and about the efficiency of planet formation. That Oumuamua might not be representative of an isotropic distribution of interstellar planetesimals, in which case we wouldn't need to account for all that much material. And indeed, Oumuamua could be a planetesimal ejected from a young nearby star, and in this case, the ejected planetesimals would not have time to distribute isotropically. A recent ejection would also be consistent with other indicators of youth. For example, the velocity of Oumuamua is only within 3 to 10 kilometers per second of the velocity of the stars in the solar neighborhood, in the local standard of rest. And this means that Oumuamua has probably been traveling for much less than a gigayear, because otherwise its relative velocity would have been higher, as the velocities tend to increase with time due to the objects encountering stars and molecular clouds. This is called dynamical heating. And is also consistent. The possible youth of Oumuamua would also be consistent with a surface that doesn't seem to be heavily processed based on its color. KBOs, hyperbolic objects, are ultra-red because of the gigayears of exposure to cosmic rays, plasma, and radiation, but Oumuamua's surface was not that red. Now I'm going to take you under the hood and explain how I got to these estimates. The key assumption is that Oumuamua is representative of an isotropic distribution. Using a detailed calculation of the PanSTARRS detection volume and the time this telescope has been able to detect objects of the size of Oumuamua, it was calculated that there are about 2 times 10 to the 15 objects per cubic parsec of a size similar or larger than Oumuamua. Using a range of size distribution, derived from solar system observations and from coagulation models, we can convert this number to a mass density shown here in purple. Now, let's see what are our expectations from the ejection of planetesimals during the planet formation process. We estimate this number using population studies, and let me walk you through one of these equations. So what we have here is an integral to estimate the mass density of objects that are in the interstellar medium. And the integral, inside the integral, in green, you have the number density of stars. Then this is multiplied by the fraction of these stars that are singles. This is in green. And then we multiply this by what is the total mass available to form solids per star. And this estimate comes from the fact that the protoplanetary disks generally have about 1% of the mass of the star, and about 1% of that material is in the form of dust, and the rest is gas. So this is where the orange factor is coming from. And then you multiply all that by what is the fraction of that material that is ejected. We assume that is approximately 1, because we know that from the solar system the ejection was very efficient and a negligible amount of material was left behind. And then you multiply all that by the fraction of stars that actually are contributing to these objects, which we assume that it is a fraction of stars that harbor planets. And then we do the same to estimate the number density, the mass density of interstellar bodies that would be contributed by stars in binary systems. And this is the second equation. And way to calculate it is very similar to what I just explained. So this is what we get when you plug in the numbers. What we expect from a planetesimal ejection during the planet formation process is at least 2 orders of magnitude below what we infer from the observations. And this is where there is that discrepancy that we still don't understand where it is coming from. And you can do something similar to calculate the number of objects expected from the release of exo or cloud comets, which is another potential source of interstellar planetesimals, as I mentioned before. Let me walk you through one of the equations. So let's look at the equation on top, corresponding to stellar encounters. As we said, the release of objects from exo or clouds could be due to stellar encounters with other stars, or could be due to the ejection of material once the star reaches the end of the main sequence and loses mass, and then all this material that was weakly bound suddenly feels less gravity and is just ejected. So focusing, for example, in the contribution from stellar encounters, the number density of bodies that would come from this origin. Again, we can estimate it using, with an integral, and under this integral, the green factors correspond to the number density of the stars that are still in the main sequence. And then you multiply that by the cumulative number of objects per star that have a size larger than Oumuamua. You see that there is a 10 to the 12 there in there. This comes from the fact that we are assuming that the exo clouds are similar to the Oort cloud in the solar system that has approximately 10 to the 12 objects larger than 2 kilometers, but we scale this to the mass of the star. And this is the orange factor here. And then we multiply all this by another factor that estimates what is the efficiency of ejection due to stellar encounters. And these factors come from dynamical simulations. And we do the same to something similar to estimate what is the number density of objects that are contributed by the ejection of planetesimals once the star reaches the end of the main sequence. So the green factor in the second equation in this case corresponds to the number density of the stars that have already left the main sequence. And then again, you multiply by the cumulative number of objects with sizes larger than Oumuamua per star. And then you multiply this again by the efficiency of ejection due to post-main sequence mass loss. That again comes from dynamical simulations. And again, when you plug in the numbers, what we expect from the release of exo or cloud objects is at least 2 orders of magnitude below what we infer from the observations. So again, we find that discrepancy. And this is when you put all the numbers together. So another big surprise, in addition to the fact that we couldn't account for as much material as is supposed to be out there based on the observation of this single object of Oumuamua. So another big surprise in addition to that is that the morphology of this object seemed to be very unusual. This object is about 100 meters in size, and it had a brightness that fluctuated very sharply every 8 hours. Some brightness variation is expected because small rocky bodies are irregular in shape, and as they rotate, their cross-section varies. So when you see a large cross-section, they seem brighter, and then when there is less cross-section, they seem dimmer. But generally, this brightness variation is small, of a few percent. But for Oumuamua, this brightness variation, as you can see in the second plot, was quite drastic, about a factor of 10. This meant that Oumuamua had a shape that was fairly unusual for the solar system, with an estimated ratio of 6:1. And you can see it in this artistic illustration here at the bottom. That comes from a Scientific American article that David Jewett and I wrote recently. So So in addition to the shape and to the number density of objects, there was something even more mysterious, and it was because upon close inspection of Oumuamua's orbit, it was discovered that the object was being accelerated like a rocket. As you can see here, this non-gravitational acceleration makes a noticeable difference in the trajectory. Red is what you would expect in the case of no excess acceleration, and blue is what you actually observe. This jet-like force is typical in comets and is caused by the mass loss that happens on the day side of the nucleus, where the ice is sublimating. So this acceleration was interpreted as a result of the expulsion of gases. And the big caveat with this interpretation is that Oumuamua never showed any evidence of gas or dust loss. In fact, the level of H2O outgassing that would be required to explain that excess acceleration that was observed in its orbit is 100 times larger than the upper limit that was inferred from Spitzer observations. The absence of dust is also problematic because the gas always drags small dust particles along, but no dust loss was found either, and dust is easier to observe than gas. So in the absence of gas and dust lost, we were left with no explanation for that accelerated orbit. There was a suggestion that this excess acceleration could be due to radiation pressure acting on a membrane-like structure of a very thin material, less than a millimeter thick. And the reason why this was proposed is because for radiation pressure to work, you need a lot of surface area and very little mass. The proposal was that this was an alien light sail. I follow up on the suggestion that radiation pressure could be the cause of the acceleration, but instead of an alien light sail, I proposed that it was a fractal structure that the one that could also provide a lot of surface area with very little mass. This that I'm showing here is an interplanetary particle collected in space. It is about 10 microns in size. Its core has a fractal structure. And what I proposed was that Oumuamua was something like this, but on a much larger scale. Fractals, I propose fractals because fractals are found in many forms of nature and are thought to arise naturally because their formation processes involve an element of stochasticity, like particle collisions in a protoplanetary disk. A fractal aggregate with a density of 10 to the minus 5 grams per cubic centimeter, again, 10 to the minus 5 grams per cubic centimeter, could provide the surface to mass ratio required to account for the observed acceleration in Oumuamua. This fractal structure could also help to explain the unusual shape of this object. But the problem, of course, is how such an ultra-low density aggregate could form naturally. This is even less dense than a graphene aerogel that, of course, is formed synthetically, right? So how can you form this naturally? There are indeed numerical simulations that study the collisional growth of dust particles in a protoplanetary disk, and they predict that if the tiny dust particles are icy and about 0.1 microns in size, the aggregates that form beyond the snow line of the parent disk will have less and less density as they grow and can have properties similar to the ones that would be required for Oumuamua to be pushed by radiation pressure. You can see in this simplified plot here in black how the density decreases as the particle size increases. So what I suggested is that Oumuamua could be one of those intermediate early products of the planet formation process that arise naturally from the collisional growth of icy dust grains. If this were the case, it would be extraordinarily exciting because very little is known about these intermediate early products of planet formation. A follow-up study by other authors pointed out that the interaction of the solar radiation with such an ultra-low density aggregate could actually explain the changes observed in Oumuamua's rotational period, and that such an aggregate could have survived the rotational and tidal forces expected during its interstellar journey. Interstellar planetesimals provide an unprecedented opportunity to test planet formation theories. The observations to test these theories are always limited to the two extremes of the size distribution: the dust in the low end and the planets in the high end. But interstellar planetesimals can give us a glimpse of the intermediate size products. In this context, the possibility that Oumuamua could be evidence of the formation of ultra-low density aggregates in protoplanetary disks is very interesting, because these porous aggregates can help planetesimals grow. Remember the meter-size barrier in planet formation theories that I mentioned earlier? So one of the mechanisms that has been proposed to favor the growth process of planetesimals is that intermediate particles are very porous, but we don't have any way to observe them in protoplanetary disks unless one of them reaches us. And this is why it would be very exciting that Oumuamua could actually be one of these intermediate products. Very low density aggregates can also help planet formation later on by delaying, for example, runaway growth, which is the process that forms the large protoplanets from the accretion of planetesimals. The second interstellar object detected, Borisov, was without question an ice-rich planetesimal ejected from the outer regions of an extrasolar planetary system. It is indeed a planet building block in deep freeze since its ejection. This is a beautiful set of observations by David Hewitt and collaborators obtained with Hubble. It looks like, Borisov looks like a normal solar system comet. It is estimated that its nucleus is between 2 to 5 times larger than Oumuamua. This is about 200 to 500 meters in size, but it didn't show any evidence of being that elongated. Its trajectory did show an excess acceleration, but in this case, it can be accounted for by gas and dust loss. It was found to be very rich in carbon monoxide, richer than almost all solar system comets. Because carbon monoxide ice is so easy to vaporize, this probably means that this extrasolar comet originated from the outermost region of its host planetary system, where it's very cold and the carbon monoxide can stay in ice form. And this is Borisov's trajectory, clearly of interstellar origin. Its trajectory was even more hyperbolic. It didn't pass as close to the Earth as Oumuamua, but it was easier to detect because of its large size and cometary activity. And on the other hand, because it has all that cometary activity, it was difficult to estimate what is the size of the nucleus. One interesting idea that has been proposed is that in the same way that Oumuamua and Borisov cross paths with our solar system, interstellar planetesimals will also enter star and planet formation regions, and in these denser environments, instead of flying through, these objects might get trapped. In the entire galaxy, it is estimated that there are of the order of 10 to the 24 to 10 to the 25 planetesimals larger than Oumuamua. If we assume that the size distribution follows a power law, this means that there is a much larger number of planetesimals larger than a meter. If planetesimals larger than a meter get trapped in significant numbers, they could act as seeds of planet formation, helping overcome the meter-sized barrier that we mentioned before and that impedes the formation of kilometer-sized objects out of centimeter-sized pebbles. Together with Colin Norman, I am currently looking into this possibility. We are studying the capture of interstellar planetesimals in 3 different environments, 2 that are representative of the earliest stages of the star formation process, and which is a molecular cloud shown in the top left, and a much more compact stellar kernel, similar to the ones recently resolved by ALMA, shown in the middle panel, and also a third environment characteristic of a protoplanetary disk that is representative of a more advanced stage of the planet formation process, which is shown here in the lower right corner. These are the characteristic physical properties of those environments. And MSN stands for minimum mass solar nebula, which is a protoplanetary disk that contains the minimum amount of solids necessary to build the planets of the solar system. So what we find is that in the molecular cloud and pre-stellar core kernel environments, only particles smaller than a millimeter can get trapped in the disk. So no particles larger than a meter can get trapped by gas track. While in the denser protoplanetary disk environments, objects larger than a meter can indeed get trapped. The planetesimals that would be trapped in these protoplanetary disks could grow quickly via the direct accretion of these particles less than a centimeter, and this could allow the mass of the planetesimals to grow by a factor of 1,000,000 before mutual collisions and erosion become important. So gas trapping in these environments could potentially provide seeds for planet formation. And what we are trying to understand now is the estimated number of seeds that each protoplanetary disk could trap, falling in the effect of gravitational focusing. This trapping mechanism could not provide the first generation of seeds, but because there is the possibility that it will have an increasingly important role later on as the number density of interstellar planetesimals in the galaxy increases with time, it might alleviate the problem of requiring all the planet-forming disks have fine-tuned conditions to overcome the meter-size barrier. The observations in the next decade are going to revolutionize our understanding of the formation, evolution, and diversity of planetary systems because of the planet surveys and these surveys that are going to be undertaken, but also because of the numerous interstellar planetesimals that the Roman Observatory will for sure discover. As I said before, it is estimated that there are about 10,000 interstellar planetesimals of Oumuamua size or larger inside the orbit of Neptune, but so far only 2 have been discovered, and they couldn't be more different. So as you can see, the discovery space is huge. These population studies that will be done with the Vera Rubin Observatory will be able to address, for example, how many interlopers are iceless and weirdly shaped like Oumuamua versus how many are like more comet-like, like Borisov. What is the size distribution of these different populations? What is their velocity distribution? What is their composition? And whether some other objects also show any evidence that could be really porous and that could be pushed by radiation pressure. Let me end up with this excerpt of the Baloo tapestry that dates back to 1066, so this is almost 1,000 years old, and it shows bewildered people looking at Comet Halley. I think it summarizes well how much we have yet to learn about interstellar interlopers. But rather than evoking fear, like comets evoke at the time, these interstellar objects evoke tremendous excitement and anticipation because they have opened a new era in astronomy in which we can dream of closely examining and maybe even holding in our hands a piece from another planetary system.